Perpetual unions got me in trouble again.
In this video, we want to talk about extension fields. So first, let's give a definition. If K is a field containing the subfield F, then K is an extension field, or sometimes we'll just say an extension of F. So what is an extension field? You just have one field containing another field. And we denote this by K over F. And I really want to emphasize that this is not a quotient. So this is K over F. This line is indicating we have these two fields, and one of them contains the other. We have the top field and the bottom field. And sometimes we'll write this instead with a diagram, K above, F below, and a line between them, kind of like the subgroup diagrams that we used in Math 206A. So just as an example, you can do this with more than one field containing another. So C contains R, contains Q. C is an extension of R. R is an extension of Q. And OK, so every field is an extension of its prime subfield. You have any field, it has this prime subfield. So it contains the prime subfield. So it's an extension of it. So sometimes when we have an extension of fields, we have this extension, which is the larger field. And then the smaller field, the subfield, would be called the base field of the extension. OK, so the next thing that I want to do is talk a little about field extensions as vector spaces. So if K over F is an extension of fields, then K is a vector space over F. And I find it's helpful to really think about why this is true. What do you need for something to be a vector space V over a field F? You need an action of F on V. This is this function from F cross V to V that we're going to denote by alpha dot V, where V is a vector in your vector space and alpha is an element of your field, satisfying a bunch of things that we've talked about extensively in Math 206 so far. So if we want to think of K as a vector space over F, what is this function, this action of F on K? Well, it's going to come from multiplication in K. So multiplication is going to give an action of F on K. So what is that? We want, for any alpha in F, we need to define alpha times beta, where beta is an element in K. But alpha is in F, and K is a field that contains F, so alpha is an element of K as well. So now we just have these two elements of K, and we can multiply them. And it's straightforward to check that this multiplication K satisfies all the axioms that you need for K to be a vector space over F. So what does that mean? Every field F can be considered as a vector space over its prime subfield. So let's just take a minute and think. There are two possibilities for what the prime subfield is. It could be Q, or it could be FP for some prime P. And what is this telling us in the case when the prime subfield is FP, this finite field of size P? Because we know a lot about vector spaces over FP. So I'll pause and erase and say a little bit about what this tells us about finite fields. Let's consider the case of finite fields. So you have a finite field, and you know its prime subfield is either FP for some P, or it's Q. But Q is infinite. So there's no way that a finite field contains a subfield isomorphic to Q. So if F is a finite field, then clearly its prime subfield has to be FP for some P. OK, so let's collect some facts as a proposition. If F is a finite field, then the characteristic has to be P for some prime P, because we know that it can't be characteristic 0, because then the prime subfield would be Q, which is infinite. So in this case, the prime subfield of F is FP for this prime P. And now we know that F is a finite dimensional vector space over FP. So if this dimension is n, then you have an n-dimensional vector space over a finite field of size P. How many elements does it have? It has P to the n elements. So what are we seeing? We're seeing that every finite field has prime power order. And OK, it's a finite field. You can multiply elements. It really is a field. But if you just think about the structure of this field as an abelian group, you know that if you have any alpha in your field, and you add it to itself p times, you get 0. This is something we talked about earlier in this lecture. So that means as an abelian group, F is isomorphic to Z mod PZ cross Z mod PZ cross 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 n times. Okay. So this dimension that comes up here, this n, is an important thing to study when thinking about field extensions. So the degree of a field extension, K over F, which is denoted by the same kind of notation that we used for the index of a subgroup H in a group G. So it's bracket K colon F. This is the dimension of K as a vector space over F. And we say that this extension is finite if this dimension, vector space dimension, is finite, or if the degree of this extension is finite, and otherwise it is infinite. All right, so in the next video, we'll talk about one particular way to get field extensions by thinking about roots of polynomials.